All right, let's get started. Welcome everybody to another lecture of the SNAPP summer course on Stein's method for queuing approximations. As usual, videos and lecture notes are going up on the SNAPP website. Anton, please take it away.
Thanks, Steve. Welcome to everyone. So last class, I got to say, I think not my best delivery in the world, but it was okay. Definitely a lot of details, and in the whole scheme of things, last class was uh, the most detailed I think it's ever going to be. So that's good news. Let me do a quick recap of the main things we covered. So last class we said given a function from defined on some multi-dimensional grid, we defined an interpolating operator A such that A times AF is extended to the reals and satisfies some properties. AF is C3. Actually, it's almost C4. And my biggest regret is not having the foresight to simply make it C4 from the get-go. And so, okay, has a weighted sum representation. So if K of X is the floor of X over delta, this is basically the bottom left corner on the grid corresponding to X, or Ki of X is the floor of Xi over delta. Then, and this is just to recap, you don't need to remember the precise form of everything, specifically what I'm writing down right now. Just have the intuition that multidimensional interpolation is done by interpolating each dimension separately. And this is probably not the best notation in the world either. I'm sure that you can improve it, but I've settled on basically this being good enough. Okay. Lastly, AF satisfies. And I'm not going to recall the properties mathematically precisely because those you can find in the previous notes. Let me just give you the rough interpretation of each property. Property number one, dAF of X is less than or equal to some constant, which depends on the dimension, delta inverse, and times norm of the corresponding forward difference. Okay. And remember delta A f of delta k, this is delta A minus 1 applied to delta f of delta k. This is delta A minus 1, f of delta k plus 1 minus f of delta k. So this definition holds in, or if the dimension equals 1. If the dimension is bigger than 1, I should have this somewhere. We say delta is the difference along the first dimension, the difference along the second dimension, and the difference along the final dimension. Okay. And I haven't defined this, I haven't written this down anywhere in last lecture's notes, so here it is. Okay, so roughly speaking, whenever we see derivatives of the function, those are really bounded by finite differences for a one between 0 and 3 and almost all a 1 equals 4. Okay, so that case when a1 equals 4 is always going to be a pain in the butt for us, but it's manageable. Okay, so number 2, AF of x acts as though it was C4 for the purposes of Taylor expansion. Specifically, the remainder term. In other words, this is not the precise definition, but if you just focus on the definition, you may lose sight of the bigger picture. And the bigger picture is that you can expand AF of x to a 4th order, even though it's not technically C4. Property number 3, this is the product rule. A applied to f of delta k times g of delta k is a f of x plus g, not plus, times a g of x plus this epsilon, which is an error term, where epsilon of x is bounded by some constant that depends on delta, and the maximum over all first order differences, delta AF, times the maximum over first order differences, delta AG. Okay, this is it. And because I really want to have everything on one page, just going to copy this over. And property number 4, basically if f is already a CS minus 1 function, so if it's already defined on the continuum, then AF of x approximates f fairly well. Well, in the sense, well, that's what I mean by it, that AF of x minus the function itself is bounded by delta. So remember, I think for intuition purposes, the main driver of what it means to be a small term is the delta. So the delta will be our scaling factor. It'll go to 0. So the higher power of s that we can get, the better. The smaller the error, okay? Which means that S comes from the smoothness of the original function. So the smoother the original function, the better we can approximate it. Up until, so for, I think it's 0. No, it's for 1. We have a limit. We cannot approximate a function arbitrarily well. We can only approximate, like once the function has more than 4 derivatives, we no longer gain any accuracy in terms of approximating things. And the intuition is that this thing only really cares about the 4 forward differences, the first 4 forward differences. This times basically the maximum over when the order of the derivative is equal to S DAF. So what I like about this notation, even though the norms are not going to be finite in all examples, they're going to be finite in our examples. Okay, so that's, if you want to understand today's class, you can just worry about the norms. That's great. Okay. All right. Now back to our class today. Interpolating, or the interpolated Poisson equation. Okay, so the goal, just to remind you, goal, we have the Poisson equation for the infinite server Q, x sub q, and this is standard equation minus h of xq. xq is in delta z plus minus r. And want to extend this thing to the entire real line so that we can plug in y instead of x sub q. And then just for the sake of being self-contained, y in our case is a normal 0. Well, doesn't have to be. Y corresponds to the generator. And the generator, we have actually 2 cases. So we have case number 1, or maybe better to write case number 0. B of x is negative mu x, and a of x, this is just 2 mu, and this corresponds to y naught. And case number 1, b of x is going to be negative mu x, and a of x, this is going to be, let's see, 2, nope, mu 1 plus 1 plus delta x maximum 0. Okay, so this truncation, again, is to make sure the diffusion coefficient doesn't go negative. All right. And x has stationary distribution of m infinity. Any questions come up so far with this recap? Let me know. All right. What do we do then? So fix h.
Hey, Anton, there's a question.
Oh, there is a question. Yes, Diego.
Yeah, maybe one quick question. I think you mentioned this last time, but you could also extend the generator and consider a different Poisson equation for the extended generator, right? And solve that equation.
Yes.
Like extend the transition rates to the real line.
Mm-hmm.
and then you get a new equation, and you can consider functions h that are defined in the entire real line. So why is it that you don't do that, and
Yeah.
you try to construct an explicit extension?
Okay. So if I understand your question correctly, you're saying, first of all, let's forget about the right-hand side and let us extend this left-hand side somehow. Perhaps we have some extension of f sub h, and we can extend the transition rates in the generator. So we extend the whole generator to the real line. And then we look at the induced Poisson equation, whatever that is, right? My problem, so I'm not saying this is impossible, but from where I stand, I don't know what the right-hand side is anymore. So at these grid points, yes, I know that the generator equals something, and that something must equal to the right-hand side at the grid points. But if you just go about extending the left-hand side in any arbitrary fashion, how would you even have a handle on what the value of it is, or what is the value of the right-hand side outside of the grid points? I
Yeah,
don't know
so
what it
my
is. Mhm.
now what I was thinking about is to extend the operator, like the g of gx, and then you have a new Poisson equation, right?
Let me write it down.
So
Yes. So
like
first, let's do this idea in green so that hopefully it's correct. I really hope you're right. And you should take all this with a grain of salt. I don't know the best way to do things. I just know one way to do things. Okay, so Diego's suggestion, we extend the left-hand side somehow, right? Magically. Well, I know that this equals, what about this otherwise? What is it? That's my problem. But I can tell you it's definitely not going to be the extension of this thing. Because just because once you fix an extension of the left-hand side, there are infinitely many ways to extend the right-hand side. And only one
yeah,
of them is going to be
but
correct. Hmm?
I don't mean to extend gx fh. I mean to extend gx, only gx, and then you have a new equation,
Hmm.
like gx tilde of something, which is the unknown,
Yep.
equals expectation of hx minus h, and you solve this new equation. So you find a new fh.
Okay, I see. So maybe that's a good way to do it. So you extend just the generator, and then you say, let me give it a new name, capital Phi.
Yeah, something like that.
Okay. I've never thought about this. So I think for the sake of time, my answer is I've never thought about this. But if, okay, ideally what we would want, we know that this thing actually, we don't need to guess at its form. I do think this question is worth the time we're spending on it, by the way. So it's an important question. Okay. We know this. Is it the case? Question mark. You see what you're doing now? You're basically making it no longer a countable state space, but now you're making it an uncountable state space. Right away, positive recurrence is no longer the right condition. You need positive Harris recurrence. So just like that, you've opened a big can of worms. Is it manageable? Maybe, right? Maybe this is a better way to do it. But for your extension or solution to make any sense, it should satisfy this new thing. Okay.
Yeah. Okay. Yeah, and
Um,
I imagine that you, in this other way, you get a lot of properties for bounding the gradients,
you
like in terms of the interpolation that you have constructed.
Let
Thank
me
you.
answer the other question, clarification, I think in chat. So in chat, I think it was with respect to property number 4, I said this only holds for S between 1 and 4. The question is, what if S is bigger than 4, then does the bound not work anymore? The point is, if F is C10, it's definitely C4. So if this holds with S minus 1 being bigger than 3, then we'll just treat it as if it's C3. Okay. So let me do that. I think everyone is sufficiently warmed up with the concepts now, which is good.
Just
Yes.
one question, Diego's question. So just as a concrete example is the idea that you might imagine extending the dynamic so that you can have a queue with half a customer, and then you have to define what that means, yada, yada. But if you can define what it means, then phi would make sense. Is that the
Right.
idea? Okay, thanks.
Yeah. But I think it's a question of, I like this idea. Don't get me wrong, but it's a question of effort. Okay. So fix H in some space. I want it to be definitely Lipschitz 1, maybe Lipschitz 1, and intersection something. And that something at the end of the day is going to come out to be, I want additional derivatives to be bounded. Okay. Let A be our operator, and let's get at it. We start with the right-hand side of the Poisson equation, except instead of the grid valued H, we look at the very natural extension A H of X. So far, we're not guaranteed that this satisfies anything, by the way. So this is X and R. Now, I'm going to say the first equality is because A applied to a constant is that constant. It's a constant function. The next equality is because A is actually a linear operator. That was never a property I mentioned explicitly, but if you want to convince yourself that's true, you look at this form. This is a linear functional. Okay, basically it's a weighted sum of functions. So A is a linear operator. Linearity of A, and this is really property number 4 that we've used in the first equality. Now we're using, and all of this is in dimension 1, so the notation is not going to be so bad. Now we're using the weighted sum representation. All right. This is weighted sum representation. Next, here we're using the Poisson equation. So I'm just going to do alpha dot 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 for the sake of time. G f sub h of delta k of x plus I. And this is sum from 0 to 4, alpha dot dot dot. Now G A f of h, maybe like this, at the grid points. So why is this allowed? This is allowed because A f h x sub q equals f h x sub q. That's why it's allowed. And I think I have enough parentheses. Next, we notice that the last thing It's simply applying a weighted sum representation to just a bunch of points. And this happens to be A applied to this function gx f sub h at the point x. So this may be confusing if you haven't seen it too many times, because I've got a lot of things. I have like an operator, a function, okay? So the way you should think of it, f sub h is a function on the grid. A of f sub h is a function on the reals. G is applied to A of f sub h. But of course, GAF, that's a function itself. Okay? And that's the function we're interpolating. So we have reached A gx A f sub h equals reals. Okay. If you're looking at this, there may be one point of contention for you, and that would be the fact that I've already defined my generator, the infinity generator. So technically the infinity has a left boundary. It doesn't extend all the way to negative infinity, right? You cannot have a negative Q length. So what I'm doing implicitly, maybe up here, implicitly, I extend, let's say, h f sub h g x f sub h somehow to negative integers. Okay, so two things why I'm doing this. Number one, the reason I'm writing it like this is because as we see it in the notes, so far, I started the class saying, suppose that the grid valued function is defined on the entire grid, both positive and negative integers. And then we can do the interpolation. To stay consistent with that, I'm going to say it's as if we're extending these functions in some arbitrary way to the negative real line, to the negative integers. And that's not going to matter so much how we extend it. But the second point why it's okay, and I want to draw your attention to this. This is maybe a subtle point. I'm using the forward differences. So if I'm interested in some point x, I basically go to k of x. K of x is the bottom left corner. It's the leftmost integer. Now, in my infinite server queue, I could say I'm interested in the reals that are the non-negative reals, in which case I am looking only at the function value on the non-negative integers. And since I'm using forward differences, it's never going to be the case that in order to define the interpolation somewhere on the non-negative reals, do I need to use the function values on the negative integers? Does that make sense? Again, because I'm using forward differences, I'm using points to the right. So it's okay actually to have a boundary on the left. But if you didn't follow that, or if you don't like that idea, you can just implicitly extend things, and that's going to be fine. All right. So there we have it. Now we have a rigorous, this is what I'm going to call the interpolated Poisson equation. And on the right, it's okay. So later on, I will show you that the right-hand side is basically the original, well, let me show you when I show you. But the point is that before we had just h of x on the right, and now we have a of h of x. And that's what we need property number 4, that a of h of x is not a big distortion of h of x. Okay. Now I want to remind you, and this we did a couple of lectures ago, recall g applied to any differentiable function at the grid points equals negative. This is our Taylor expansion. Okay. This takes you back, but this is, you can say, where do I see this, or where do I see this in the notes? This is when we were doing the Taylor expansion on the Markov chain generator, which was lecture 3, I believe. Plus, minus. And I do want to be precise because I want a fully rigorous worked out example. That's why I'm going to be dragging things out fully here, or expanding things out rather. Plus the death rate times this epsilon minus. So epsilon plus epsilon minus defined in lecture 3 notes. Okay, but really, this is the last term we're going to worry about. Okay. Good. So this is the Taylor expansion. And what's going to happen now, that is what I've just given you, the expansion of this grid valued function. And now I want to apply my operator A to it. Now, in an ideal world where if we could play God and we could make things whatever we want them to be, we would love it if the extension, let's say, of this first order term was simply equal to x a f sub h prime of x. We would love it if that were the case, but it's not, at least not according to our operator. So now, and why does it matter? Because this is what appears on the left-hand side of the equation. So what we're going to do next is we're going to go through these things term by term, and we're going to apply the interpolation operator to each of them, and we're going to see what we get. And that's going to be basically applying our properties 1 through 4 over and over again. Okay, so apply A to each term in expansion of G A of sub H. Okay, case number 1, or term number 1. A applied to this thing negative mu x sub q a f sub h prime. So I'm not going to write these parentheses anymore around a f sub h, but I just want to do it once. Okay. How does this interpolated function look like? Okay, now we're going to do product rule. Why do we want to do product rule? Because this is one function, it's a linear function. This is another function. So product rule, and this is property number 3. This is equal to negative a of x sub q of x. So I'm doing it this funny notation. I'm basically, like, instead of reintroducing more notation to define this linear function, I'm simply treating this x sub q as being a function, which is the identity function. A applied to a f sub h prime at the point x. And of course, I have a negative mu. The constant gets pulled out. The constant gets pulled out because A is a linear operator. Plus the product rule error term. Okay, so one thing at a time. Let's say 1.1. A applied to a f sub h prime of x minus a f sub h prime of x. So this is, again, I already had a differentiable function. How much does my interpolation distort it? And ideally, I don't want this to be much. And this is what I use, let's say, property number 4 for. So by property number 4, we know that AF sub H prime, we know that this is C2. Why is it C2? Because AF sub H of X is in C3. Okay, that's why it's C2. So we're going to use property number 4, where S minus 1 equals 2. So on property number 4 with S equals 3. And if you do this, believe me, you will get some constant times delta squared times the norm of AFH triple prime of X. Okay? Let me, one time, because this is our first time using it, and this is the first time where you're going to want to double check that what I'm saying is correct. So let me one time copy paste it. All right. So what I'm saying is this F is going to be AFH prime. We know this F is C2. So then I can invoke property number 4 with S equals 3. Right. Yeah. We can actually get away with delta cubed. So we can actually do 1 order of delta higher if we use the 4th derivative. Okay. Good. So that's property number 4. 1.2. This is A applied to X sub Q of X equals, what is it equal? It equals to X. Also by property number 4. Basically, X sub Q is a linear function, and we're going to interpolate linear functions perfectly. The last thing, this error term, epsilon subproduct rule, and this is going to be bounded by constant times mu. The constant comes from, this is property number 3, the product rule. The mu comes from this constant over, this mu over here. And what we had was the norm of delta 1, or just delta, applied to X sub Q times the norm of delta applied to AF sub H prime of X sub Q. Okay, now this is simply X sub Q plus 1 minus X sub Q, which equals delta, which equals not 0, equals delta. Okay, so this is the difference of having one extra customer in the system, but of course everything is scaled by delta. And this is like the mean value theorem, delta times the norm of AF sub H double prime. Okay. So this is, let's call it mean value theorem. And all of this stuff has been rigorous. That's the point I want to make. So as a result, this thing, well, maybe that wasn't necessary, but A applied to negative mu X sub Q AF prime of X is negative mu X AF prime of X plus some error, where the error is bounded by the error term is less than or equal to, let's see, we had basically a delta squared everywhere. So this is the first error term. So some constant delta squared, the norm of the third derivative of AFH, and also we had the norm of the second derivative showing up over here. So long story short, we recover exactly what we were hoping for. And the error term is not so bad. This should be familiar to you now, okay? Because we have like a delta squared. This is going to be the rate of convergence. And we have the constant term in front of the rate of convergence. But we've already seen these derivatives. These are second and third derivatives of the Poisson equation solution. Interpolated. So this is a familiar form. Okay. Now I went term by term on this one. I'm going to speed up a little bit on the following ones. This was our second term, negative mu 2 plus delta x sub q. You can think about the truncation as well if you want to. And by the same logic, it's going to be 2 plus delta x. So this is for x bigger than or equal to 0. Just to clarify, where x sub q bigger than or equal to delta 0 minus r. Oh, not bigger than 0. Just keep it like this. X bigger than or equal to negative delta r. That's the right one. Triple prime of x plus an error term. And let's quickly convince ourselves that we understand the error term. So the first thing we want to say, okay, we're applying a to the product of two functions again. This function is linear, so a applied to this function is the linear part. A applied to AF triple prime, well, that's going to be just AF triple prime plus some error term. And what is the error going to look like if you sit down and do it? You're going to get less than or equal to C times delta squared AF sub H for derivatives. There was one critical thing missing. And then because you might be questioning, where did I get those two extra deltas, or where did I get the delta squared from? So I got the delta squared because I actually have a delta squared multiplying this whole term that I have selected. So we see, and maybe over here. I can write original term. All right. Okay, so it is enough to bound. Oh, sorry, folks, this is a typo. And okay, let me correct the typo. I copy pasted the wrong thing. So let me slow down at the risk of confusing myself. I rushed ahead to the third order term when really I was working with a second order term. There. And that's why it makes sense now. So it's for the original term. There we go. Okay, now it makes more sense. Basically, we're saying AF double prime, it's almost C2. So if AF is almost C4, AF double prime is almost C2. Okay, and that is how I get the extra delta squared coming out here. There. I think I confused people, so let me pause here if there are any clarifications. This is B3 here, right? But the point is, again, this looks like some rate of convergence, delta squared, and a derivative term. Good. And then with the remaining two terms, we're going to be very crude because the first two terms mattered because I want to know what their extension is because that's what's going to define my diffusion generator. With the last two terms, they're going to be error. I don't need to be so careful with them, so delicate with them. That's why I'm going to apply A to all of them, but I'm just going to be a little bit cruder in terms of bounding them so that I don't make any more mistakes copy pasting. And next. A applied to all of this thing at the point X, okay? The delta squared comes right out, the mu comes out. Delta squared mu over 6, A applied to X sub Q, A sub H prime of X, well, X. Okay, now here's where I'm going to appeal again to the weighted sum representation. If you want to analyze this term, you could again use the product rule and then all of these four properties to bound these things, but that's unnecessary because you're not going to get a better bound. You're not going to be able to squeeze an extra delta out of it. All of the deltas are already squeezed out of it. So really, we want to bound this by some constant term, okay? Constant factor. And the way to do it is basically using the weighted sum representation, delta squared mu 6. So my claim is that, well, let's see. I goes from 0 to 4. I have the weights, which don't really matter so much. K of x times, let's see, it'll be x of k plus I. That is this term. So I'm switching the q's to k's here. A f sub h triple prime of xk plus I. Okay, now let us simply replace this by the norm of the third derivative. That's like a universal bound. And what do I get? I get that this whole thing is bounded by delta squared mu over 6. A applied to x sub q of x. And this is just x. And then we have a norm of the third derivative. In other words, we have some constant times mu delta squared. And we have absolute value of x times the norm of the third derivative. Okay. Let me go back in time. It's easy for me to do. Maybe not so much for you, but here we have the derivative bound. So what I'm doing is I'm gonna go back to when we were doing it the original way, the generator approach. And I want to just show you that we are looking at the same thing from a different angle. So here, this was the third order term we were tackling, okay? And the error term, see if I can find it. This was it, right? We had 1/6 delta squared mu. We had something linear in the state x, and we had the third derivative. Okay, modulo a constant, modulo the constant, this is the same thing. That's the whole point. We've done all of this so that we can get similar looking error terms. Okay, and the last piece, just recall very quickly, for example, and I'm not going to dwell on this too much, but I just want to write it out. Okay, so very quickly, if we want, again, a rough argument of how to bound epsilon plus, this thing, of course, is going to be replaced by a f sub h triple prime of y minus a f sub h triple prime of x minus. And this by property number 2. This is property number 2. This is where I'm saying, well, it's as if a f triple prime was differentiable for the purposes of the mean value theorem. This was less than or equal to, we have y minus x norm a f sub h quadruple prime. So then in this epsilon, we basically have the norm of the fourth derivative. Now, x and y, they are at most delta apart. X minus y is less than or equal to delta, because y is in x plus delta. Okay, so now we have that the epsilon plus of x is less than or equal to 1/2 integral from x plus delta, x plus delta minus y squared. We have another x minus y, and we have the norm of the fourth derivative, fourth dy. And this is bounded by delta. This is bounded by delta squared. And we have the integral, which gives us another order of delta. So at the end of the day, there is some constant delta for a f sub h fourth derivative. Same for epsilon minus. F sub h. I'm going to summarize all we've done in quite some detail. I'm going to summarize what we've done in just a moment. There's one thing I'm not going to do, but I'm just going to ask you to believe me. When we had the epsilon plus and epsilon minus, in front of the epsilon plus, we had a lambda, which is a constant. So when we apply the interpolator a to epsilon plus, the lambda comes out and we use the bound we derived. Here we have the death rate. But again, this is a linear function. This is a linear function in x. So if we apply the a applied to both of these things, we again use the product rule, and then we use the uniform bound on the epsilon. So it's manageable with what you've already seen. Where am I? Okay, summing up. Okay. For x bigger than or equal to negative delta r. Where is this negative delta r? Because we said x sub q is bigger than or equal to x naught, which is negative delta 0 minus r, not negative delta, simply delta. Okay, this is the normalized version of the zero customer state. We have done all of this. Why is it for x to the right? Because over here, okay, this object is defined for x bigger than or equal to, this object is, without further extension, this object is defined only for the states where there's 0 or more customers in the system. So we just worried about that portion of the state space first. Okay. That's why x is big. Okay. We have a applied to g sub x equals negative mu x a f sub h prime plus 1/2 mu 2 plus delta x. But because we're in this part of the state space, it actually is equivalent to 1 plus delta x maximum 0. Okay, you can convince yourself that's true. But again, not the main focus. Plus x plus error term. And this error term, at the end of the day, if you collect everything, is less than or equal to, let's see, we have c mu. We're going to have like a linear term in x, for example, that comes from our bound on the third derivative term. And I've really not given myself enough space. Okay, maybe I'll write it here. The error term less than or equal to c mu 1 plus x plus 4 delta. If delta is less than 1, then the 4 delta can get absorbed into the constant. Delta squared times f sub h double prime and a f sub h triple prime, a f sub h quadruple prime. Again. Okay, and this holds for x bigger than or equal to negative delta r, which is negative squared. Okay, any questions? This is a good place to break. Clarifying. Okay, summarizing again what we've done. Number one, after we have our new toy, the interpolator, we made sure that the Poisson equation has been extended to the reals. Or if you want to, you can be picky and say, well, so far we've only extended it to this domain. The right-hand side of the Poisson equation, well, there's not much to do, okay? The left side of the Poisson equation, it's not clear to us, especially because here is the Poisson equation. We want to do Taylor expansion of this left side to extract a diffusion generator. It's not clear to us what the circle term is exactly. We know, of course, its value on the grid, but now we need to apply the interpolating operator to the Taylor expansion itself. And this is where you're going to be using these properties P2, P3, P4 a lot. The product rule, basically the product rule everywhere. After doing that, and being very careful to keep track of the error, we get that our interpolated generator looks like the natural candidate, right? This is what I always wanted. I always wanted to replace those x sub q's with x's. But I can only do this at the expense of extra error. So this error is really interpolation error. And it has nothing to do with the quality of the diffusion approximation. This is the price you pay for discretizing, basically, right? This interpolation error is totally independent of any diffusion generator so far. Okay, but the appealing thing about it is that, look, it depends, like we've already seen, on x in like some linear fashion. So if we want to bound this is where the moment bounds come in. It's got a delta squared, which is actually usually we've seen order delta rate of convergence, 1 over square root of r. So here it's got a delta squared. In other words, it's not going to be the bottleneck, right? It's not going to be the one saying, oh, well, you can only show a weaker rate of or a slower rate of convergence because the interpolation error is tripping you up. But of course, it is going to be a bottleneck if you want to show any rate of convergence beyond delta squared. And the third thing are these derivative bounds, or the Stein factor bounds. And again, how do I relate this to, let's say, the Stein factors for the infinite server queue? That's where property number 1 comes in. That we're gonna see that. And I think, judging by our pace, it's going to be the topic of next class. All right, so that's where we are, and that's the kind of picture you should have in your mind. Now we're going to do the final step, and we're going to finally substitute, instead of the little x, we're going to substitute our diffusion term. Okay, final step. Let me start with expected value h of x minus expected value h of y. Not a h of y, just h of y. The first thing we're going to do is we're going to do a triangle inequality, h of y minus expected value a h of y plus expected value h of x minus expected value a h of y. Why are we doing this? Because our entire derivation actually was for the second term. Of course, initially, right, say h is a Lipschitz function. So we're going to start by assuming we have an extended version over the entire real line. And then this thing makes sense. And we really want to look at the Wasserstein distance between x and y. So we're going to write it out in 2 parts. And here is where property number 4 is going to come in handy again. because we're going to say, well, presuming H was sufficiently smooth, how much are we distorting it by considering the interpolated version? And this you want to bound using property number 4. Now, if H is Lipschitz 1, meaning let's say H is just C1, right? Property number 4 is going to give you an upper bound on this of order delta. Just delta. Therefore, order delta bound. If H is in Lipschitz 1 and H prime, let's say, is in Lipschitz 1, so bounded first and second derivative, therefore we get order delta square bound. Okay, and you keep this in the back of your head because for what we're going to do next. Okay. Okay, so of course we're going to focus on the second term. Second term, we're going to be very clever about how we split it. And this splitting of the state space is going to be useful for you in other settings as well. Basically, we say, look, the diffusion, the Y, I didn't define what it is yet exactly. It's some diffusion process, but the diffusion process is going to live on the entire real line. And the Markov chain only lives, you cannot have negative customers. That's the way I'm going to say it, right? So in some sense, even without any fancy interpolation, not relying on anything we did, there is a portion of the state space of Y which X will never get to because X is not defined. And that's exactly this portion of the state space. So there we have to say, well, what do I mean exactly by H of X? Okay. Well, sorry, no, H of X is a constant in this case. But there's a portion of the state space it'll never cover. In other words, we cannot hope that Y approximates X accurately on this part of the state space because X doesn't go there. So how do we get by? How do we not get stuck on this being a huge error term? Does anybody see? Right? It's because this part of the state space is so rare. Indicator Y is less than or equal to negative square root of R. So in any for the asymptotic regime to make sense, R needs to go to infinity. And I'm going to show you basically very simple. It's just some concentration inequalities using Markov inequality, for example. You can use to bound this thing, provided you know that Y has bounded moments that are independent of R. So I'll go into that detail. Okay, but my point is this first term exists not because of the funny way we interpolated, but it just exists because the diffusion is defined in a portion of the state space that the Markov chain is not. And this is the one we can do something about. Okay, so this is term number 1, term number 2. Okay, so let's see for term number 1. Yeah, we got just enough time. Let's bound term number 1. Okay. Use the fact that Y is less than or equal to negative square root of R is a very rare event. For example, if we know that expected value of Y to the power of M is bounded by some constant where Cm is independent of R, then for any n less than m, I look at the expected value of y sub n, indicator y less than negative square root of r, is bounded by delta m over, oh, let me write it, stay consistent. Expected value, 1 over square root of r to the power of m minus n, y m minus n, y to the power of n. And of course, we can even add in the indicator. Well, we should not. We cannot skip it. Got the indicator there. And this is just bounded by delta m minus n times c to the power of n. Okay. Basically, what it's saying is that if you know like the 100th moment is finite or is bounded independent of r, you can make this term arbitrarily small. Okay, so in practice, we want, for example, let's say m equals 10. That's safe. That's more than we'll ever need. M equals 10. Okay, and then we say n equals 1 or n equals 0 or whatever. Or maybe n equals 5. Even with n equals 5 and m equals 10, we have a delta to the power of 5 here. So the point is, this is a term you guys can easily sweep up. It doesn't really depend on any Stein's method techniques. This is just concentration bounds. And then to really, how do we get the moment bounds? So remember gy of f of x we have is negative mu x f prime of x. This is y naught, mine plus 1/2 2 mu f double prime of x. This is y naught. You don't even need to look at it for a Lyapunov function to see that the moments of this are bounded by a constant independent of r, because there is no r, right? There is no r on the right side. For gy1, it's similar. There is an r on the right side to mu 1 plus 1 delta x v naught of double prime of x. There is an r on the right hand side, but can use Foster-Lyapunov condition. Can use Foster-Lyapunov with the test function v of x equals x to the m for m even to get expected value y m is bounded by some constant, depending on that. Okay, so if you're looking for a homework exercise, you can try this out yourself, but it's there for completion. So that's term number 1. Well, term number 1, that's really dealing with this indicator. What about that's, we didn't talk about exactly binding term number 1. We talked about bounding the probability that this happens. So now what do? Well, you say this thing is a constant. Okay, so a constant times this probability, we can make that arbitrarily small. This thing, if h is Lipschitz, then this grows at most linearly. And then we have absolute value of y times this indicator, so that probability is small too. Okay. Okay. I wanted to copy paste this. So we're back here. Now, we need to verify that Ito's lemma holds, or the regularity conditions are satisfied. Okay, so this is always the step in the generator expansion. This is the BAR, or the stationary equation. We need to verify that, there's a regularity condition that's satisfied. This goes back to lecture 1, but it's not that hard to do. It's not that hard to do, but a priori, without knowing f sub h, you cannot verify this yet. So you need to say, okay, reminder, I need to verify this thing. And I'm going to add and subtract. I'm going to subtract the 0 rather, not add and subtract. So then this is bounded by expected value EH of x minus AHY minus GYA f sub h y indicator. We're outside of the state. We're on the edge, or sorry, we're outside of the region defined by x. So I did jump the gun a little bit by bounding term number 1, but that's not critical. I did jump the gun because remember, if we have this term and we want to subtract the 0 from somewhere, well, we need to look at the expected generator on both domains, right? So we cannot just cherry pick the domain that we like. Okay, that's fine. We do subtract in both domains. So remember my conversation about how to bound this thing? Well, this doesn't change. This is a constant. This is at most linear in H. And once we pin down the derivative bounds on f sub h, you can show very crudely that this grows like some polynomial in y. Okay, those are going to be some crude bounds. But really, we want to bound term number 2, and that's where I'm going to focus on. For term number 2, we've done all the hard work already. And I want to show you this by copy pasting it. Term number 2. This equals the expected value of, not the expected value, this is the generator, A applied to the generator of f, A, f sub h, y. Right? That was the first part of the lecture today. Okay, so this is the generator, the interpolated generator of the Markov chain. And we did a Taylor expansion on this. So A, G, X, F sub H, Y. I'm missing an A. For Y less than or bigger than negative delta R, we have the Taylor expansion. And we've already bounded the interpolation error terms. Great. And the high order terms as well. And now we just need to pick our diffusion generator. if we pick y naught, such with the drift negative mu of x, a of x is equal to 2 mu, then number 2, basically we're going to kill the drift, we're going to kill this component of the second order term, and then number 2 is bounded by whatever error terms we've already established, plus this delta x second derivative term. Delta y a sub f double prime of y plus, I regret calling this the interpolation error because that isn't fully accurate. And I'll have a few minutes to fix what I meant. Okay, so if we pick y naught, then we have this error term, and this is like delta squared times the derivatives. If we pick y1, so that's b of x is negative mu x, a of x is 2 mu 1 plus delta x maximum 0, then number 2 is simply bounded by the previous error. Okay. We're done as far as writing goes. Let me just give some commentary. First of all, we haven't finished our bounds. We suspect that this grows like order delta. We suspect that this grows like order delta squared, but to verify this, we need a bound on the first moment of the diffusion, and we need a bound on these derivatives. Now, for a bound on the first moment of the diffusion, actually, I gave you the procedure, the Foster-Lyapunov. This is the same as for the Markov chain. And in most cases I know of, actually in all cases I can think of right now, if you have a Lyapunov function for the diffusion, that same Lyapunov function works very well for the Markov chain as well, in terms of establishing these moment bounds. So the order of difficulty of bounding these moments is similar or comparable. And then we have these Stein factor or derivative bounds. Remember when we were doing things from the perspective of the diffusion Poisson equation? We worked very hard, I believe it was lecture number 4. Let me just get us towards the end. There. We worked very hard in lecture number 4. We did these derivative bounds for the y naught diffusion, for the first diffusion. And then we established some upper bound in the Wasserstein distance. And then we changed the diffusion approximation a little bit, right? We went from y naught to y1. And then we saw, oh, I need to rederive all of my derivative bounds, or I need to rederive all of my Stein factor bounds. And that was painful, just because it's bulky. So with a prelimit approach, the benefit is, look, the capital F doesn't depend on the approximation you're using. In other words, you need these derivative bounds only once. It's a property of the Markov chain. And whenever I talk about this, I want to promote the notion so these are called Stein factors from the Stein community. I want to say that for every Markov chain, it has its own Stein factors, okay? And these are a fundamental property of the Markov chain because they dictate how well the diffusion approximates it. So to me, it should be up there with like the second largest eigenvalue modulus, right? For every Markov chain, we know that the second largest eigenvalue dictates the rate of convergence to stationarity? Well, the Stein factor balance should also be an important property of the Markov chain. Good. Next class, we're going to focus on how to actually bound these Stein factors. That's the final piece of the puzzle. And then when you see that, you will be able to fully distinguish between the prelimit approach and the original approach. That will be the last piece of the puzzle. For the last few minutes, I just want to correct myself, okay? Because I called this just the interpolation error. Actually, I was mistaken. It's not. All of this includes both interpolation error terms and actual diffusion approximation error terms. So when I went and I did the Taylor expansion, I had these third and fourth order terms, okay? These are the diffusion approximation error terms, okay? Because when you take away the diffusion generator, this is what's left over. So this is the error of approximating things. The error of interpolating comes about when we're doing like the product rule, when we're applying the interpolator to this circled object and we're applying the product rule, and we're getting all these like artificial error terms. Those are the interpolation error terms. Okay, so there's a slight clarification of what I meant. Okay, all right. So coming back, the topic of next week is going to be, we're going to start with establishing Stein factor bounds for the Markov chain. I'm going to talk a little bit about the MM infinity Q, and then I'm going to talk, maybe start there. And after that, we will have completed like the core portion of this class, of these series. After I talk about the prelim approach, I'm going to do a very important example in multiple dimensions, because so far we've been restricted to the one-dimensional setting. And in the one-dimensional setting, despite the amount of time it took us to get here, this is lecture 6, so this is already 9 hours into it. The one-dimensional setting is usually child's play when it comes to comparing it to the multi-dimensional setting. You just need not totally, you need much heavier machinery to handle it. So it's very important that you see at least one multi-dimensional example worked out. And I think that'll take us into week 4, and then we'll see where we are as far as week 5 content. So let me stop here and take any questions. Does the error term of epsilon plus need diffusion bounds? So I think in full generality, I think yes. Let me go back to it. So 2 places where it does. So this epsilon plus really only depends on the 4th order derivative. Now, when it comes to the 4th order derivative, generally speaking, in most of the cases I've seen, it's going to be boundable by a constant, like a constant bound. But suppose it's not, it's plausible. I'm sure there is an example where this thing is bounded, let's say quadratically, right? So you cannot just bound it crudely by the norm. So if the 4th derivative grows quadratically, you're going to have, in this bound, you're going to have a term that depends on like bounded by x squared, okay? And then when you go back and apply the expected value with respect to the diffusion, it's going to be like this x squared term is going to turn into the second moment of y, of the diffusion. So in that sense, the epsilon plus may need diffusion-related bounds. But in this example, it's not going to depend on it. But also on the epsilon minus term, now that you mention it, right? Here, the epsilon minus component will need an explicit diffusion-related term. Why? Because the death rate is a linear function. So you're going to need to control the first moment of the diffusion. So there are 2 components. It's the Stein factor bounds, the derivatives bounds, and the transition structure of the Markov chain, which dictates what exactly does your error depend on. Okay. I think that's it. Sounds like that's it in terms of questions.
All right, thanks everybody. See you as usual next Monday.